be looking at thermal stresses and strain, right? Thermal stresses and strain. We said in our introductory class, our introduction, the first class we had on strength of material, we've defined the word strength of material. We've made mention a lot of terms, right? A lot of terminologies. We've highlighted the terminologies we'll be using in strength of material. And of course, you would have seen that we've made use of few among them, right? Now, continuation from where we stopped. What we did previously is what? Thermal, it is stresses and strain, right? What we did previously was what? Stresses and strain. But here now we have what? Thermal stresses and strain. Meaning that what you've learned as far as stresses and strain is concerned, you are bringing it to what? Thermal stresses and strain, right? But we are going to look at thermal stresses and strain in two aspects. Meaning that just know this. When you see a topic or when you see a subtopic generally, always understand the in-depth behind that topic. It is, or let's say, always understand what the definition says. It is the definition that will serve as the basis of that topic. Now, when we see thermal stresses and strain, what can we say? You know, I'm familiar with stresses and strain, right? I'm also familiar with thermal. What does the word thermal means? Temperature, right? You know, earlier when we discussed stresses and strain, the whole concept is that I'm applying an external force, right, to a body. You know, me applying an external force to a body, I will have, depending on the external force you are having, I'm going to have either elongation or contraction, right? If you have elongation, you know what it means. You've applied tensile force. If you have contraction, you know what it means. You've applied what? Compressive force. But the question now is that, you know, I applied external force. What if an external force is not applied to a material? Can this material has increase in length? Can this same material has decrease in length? Are you getting me at all? And the answer is yes. So that's what thermal stresses and strain is saying. By the word thermal, we can relate it to what? Temperature. By the word stresses and strain, the whole idea is that increasing and decreasing. So what it means is that when you have a body and this body is subjected under temperature, we can have what? Increase and decrease. We can have what? Increase and decrease. A real life scenario. Let's say you have a metal. By the time this metal is heated, well, what do you think is going to happen when you heat your metal? When I say heat, meaning H-E-A-T, heat. Are you getting me? By the time this metal is being heated, what do you think is going to happen? During the process of heating, what will happen? It will expand. When it cools off, what will happen? Short. So we are saying that without an external force being applied on the material, you can still have both tensile, meaning elongation, and compressive, meaning contraction. Are you getting me? That's the meaning of thermal stresses and strain. So in general, or you say by definition, what does thermal stresses and strain simply means? From the whole explanation we've done, you can simply define thermal stresses and strain. You can simply define thermal stresses and strain as the elongation or the contraction that occur when heat is being subjected on the body. I said with the whole explanation or with the whole idea is that you can simply define thermal stresses and strain as the elongation or the contraction that occur in a body when this body is subjected to heat. When heat is subjected, or when this body is subjected to heat. You know, we are saying stresses and we are saying strain, right? Now, what we just did here, or that definition, is only buttressing more point on what strain means. Are you getting me? Or is only defining what strain means. By the word strain, what do you mean by the word strain? Either increment or decrease, right? We are not saying that when this body has been, we are still going to see diagrammatically, meaning by illustration, we are still going to see it. But I want us to understand, we are not saying that if this body is being heated, we are going to have elongation, during the process of heating, right? And you are going to have contraction during the what? Process of cooling. That's for strain. That's what strain means. Thermal strain, right? Now, thermal stress. We said when a load is subjected on a material, the body, or when a load is subjected to a material, stress is said to be induced. Are you getting me? Stress is said to be induced. Meaning that, same idea, when this body is being heated, thermal stresses is induced. Or stress is induced. The type of stress here is called thermal stress. Are you getting me? Now, we've seen the concept, or we've seen the idea that our body can increase and it can also decrease. How does it happen, or how does it occur with this thermal stress? Meaning, in some cases, regardless, by the time we heat this body, it is expected to expand and it is expected to contract. In some cases, we can have that, while in some cases, we might not have it. Do you now know the difference why we are having, in some cases, we are having elongation and contraction, and in some cases, it does not occur like that? Do you know why? Do you know why? No. Do you know why? No. No. All right. Let's see by illustration. By illustration. By illustration. Let's say you have a metal rod. Let's say you have a metal rod. Say this is A. Say this is what B. Why I'm doing all this is that unlike normal stresses and strain, whereby the question just says that calculate the length, calculate the change in length, calculate the force, calculate this, calculate that. Question will come directly. But this one, you have to understand the English that the question is saying. Are you getting that? You have to understand what this question is saying. Meaning, question will not just come direct and saying calculate length, calculate change in length. That's it. That's why we need to understand all this. So I'm saying that by illustration or diagrammatically, we'll be considering two scenarios here. The first one is when the both end of my body is free. I'm using a metal rod. When the two ends of my metal rod is free, right, are free. Then the other one, when the two ends, they are fixed. We've seen the concept now that you having a body, stresses is induced, right? These stresses that's induced, or these stresses that occur, is what will make your body to elongate or to contract. We are not saying that, let's consider case 1, when our body is free. Case 2, when the both ends are fixed. So by that, this is what I'm saying. Say you have A, you have B, and this body is being heated. This is case 1. This is case 1. I said you are going to understand thermal stresses and strain in two aspects. So this is the first aspect. Then the other aspect, you are going to see that too. You are going to relate it to what? Linear expansivity. What did I say? Linear expansivity. Do you still remember what linear expansivity says? Yes. It is the what? It is the ratio of change in length to the original length multiplied by the distance, right? So we are understanding, or by definition, what does it say? The degree rise. All right, mathematically, linear expansivity. Hello, linear expansivity is the ratio. It is the ratio of change in length to the original length multiplied by change in temperature. So I said that we are going to understand thermal stresses and strain in two aspects. This is the first aspect. Me using a practical illustration saying we have it, we have this, we have that. The other aspect is that we are going to understand it in terms of what? Linear expansivity. What we are doing here, we are going to derive a formula. By the time we derive this formula, by linear expansivity, we are going to see how we derive this formula. Are you getting me? We are going to see how we derive this what? Formula. Now, from here, let's note this. He said this is case 1. This is what? Case 2. This is case 2. You are having the same metal rod. This metal rod, say it is fixed. Say it is fixed. Say this is A. This is what? B. This is it. This is case 1. This is what? Case 2. your case one, what can you see in your case one? You are seeing that you have a metal rod, and this metal rod, what do we define when it comes to thermal stresses and strain? It simply means elongation and contraction simply occur when a particular body is subjected to heat. We now said case one, I'm having this body, in this case a metal body, which is a rod. So this rod is subjected to heat, right? Yes. As this body is subjected to heat, stresses have been induced, right? With these stresses, as this body is subjected to heat, stresses have been induced, right? Or before then, this body is it going to increase in length or decrease in length? Increase in length. It's going to increase in length. Why? During the process of heating. Now let's say you have this. Let's say you have this. Initially, I'm having a length as this, right? N meter. But now, due to heating, I'm having a length as this, change in length. Are you getting me? I'm having change in length. My question is that, don't forget, stresses have been induced. Stresses have been induced. These stresses that have been induced, what has this stress done to this body? It increased the length. That's it. These stresses have what? Increased the length. Meaning the stress induced due to the process of heating has increased the length. When this same body is cooling, what happens? It contracts. Now you are saying you have two parameters. The first one is what? Change in length. Right? The second one is what? Length. The third one is what? Linear expansivity. Just that every material has its what? Linear expansivity. Every material has its what? Linear expansivity. Now we are not saying that we've seen the concept on how this works when the two ends are not free, right? Using same idea, let's say this very guy has been heated. Will this elongation occur? Will this elongation occur? I'm asking a question now. Hope you are following me. I said, come back to case 2. Come back to case 2. From case 2, this same body, this body that you have here, you see the same body you have here. Yes. The same concept here. You see the same concept here. I'm not saying that this body, what made this body to have an increase in length is due to the stresses that have been induced in this body. Same stresses have been induced in this body. But the question is, the way this guy increase in length, can this guy also increase in length? Why? It is fixed. Because it is fixed.
Okay, that's why it's cracking, of course.
Because it is what? Fixed. That's why you have cracking.
Yeah.
That's why you have cracking. That's what you are trying to say. That's why you have cracking. Are you getting at all? Yeah. So that's it. So we are saying that for this guy, this body cannot increase, or there is no increment for this body. And if there is no increment, will there be decrement? Are you going to have decrease? No. Meaning the stresses induced, you just have it. It is not affecting the body. Hope I'm communicating. Yes, all right. Now from here. So this is what it means when we say thermal stresses and strain. You can see how temperature has affected your body to increase in length and to contract. Right? But the word we use here and the word we use here, they are different. Meaning you'll be given a question. Question 1A, find this. Question 1B, find this. What are they saying? This one is called free expansion. But this one is called what? Free expansion. Why do I call it? Free expansion. Free expansion. Why case 2? Meaning the expansion has been prevented, right? Meaning what? The expansion has been what? Prevented. So right. Okay, expansion prevented. Or let me just put it better way. The expansion has been prevented. Are we communicating? Yeah. Alright, that's the meaning. Now, we've seen from case 1 that the expansion, it is free expansion. Case 2, the expansion has been prevented. Case 3, partially prevented. What did I say? Case 3, partially prevented. Meaning that what we are saying is that if we have, or if we can have case 1 as free expansion, case 2 prevented, we can also have partially prevented. We can also have what? Partially prevented. So meaning all of this has its own formula. All of this has its own formula. Case 1 has its own formula. Case 2 has its own formula. Then case 3 also has its own formula. So let's see the possible way we can derive all this formula. Now from case 1, we have 3 parameters, right? And these 3 parameters, change in length, original length, the linear expansivity of a material. Mathematically, the change in length of the material under thermal stresses and strain, you have it as change in length is equals to linear expansivity multiplied by the length multiplied by change in what? Temperature. Change in temperature. Any question so far? No question. We've seen that we can have a body. When this body is subjected to it, we can have free expansion, we can have prevented expansion, and we can also have partially prevented expansion. Now, with all of this, let's start writing our mathematical formula, or you say our mathematical equation. What's the question? I don't know. You see that in question. You see that in question. Okay, how do you illustrate it? Let's say you have this, probably. Let's say the total length. Let's say the total length of your rod or your material is 9 meters. And question given says that it is partially prevented. It is partially prevented at a distance 6 meters. What does it mean? You are left with 3 meters. Meaning the total length, which is 9 meters, they have prevented 6 meters. Diagrammatically, how do you express it? You have this. Is that not correct? It is. He's the one that asked the question. Are you getting me at all? I said he asked a question that how do we illustrate the partially prevented? I'm not saying that the whole idea of partially prevented is that let's say you have a total length 9 meters. Our question given says that it is prevented partially at a distance 6 meters. Diagrammatically, how do you write it or how do you illustrate it? This is your illustration. You are saying you are combining case 1 and case 2, saying that this is your case 1 and this is your case 2. Saying for case 1 it is prevented. This case 2 it is freely expanded, right? Free expansion. Where the total length is what? 9 meters. So all of this, we just need this just to understand the theoretical explanation and the practical explanation and the what? Practical explanation. That's what we are saying. Now from here, I said up to this level, since we have these 4 guys, this is change in length, original length, linear expansivity, right? We've seen how we derive all of this. We also have change in temperature. We are not saying mathematically change in length is equal to the linear expansivity times the length times the change. Linear expansivity times the original length times the change in what? Temperature. Call this equation 1. Call this equation 1. From equation 1, this is just my change in length. Let's bring this back to normal stresses and strain. From normal stresses and strain, we've discussed some parameters which are what? Change in length, strain. This is represented as what? E. This is not E, epsilon, right? We have sigma. This is what? Stress. What do we have again? I guess that's what, right? Then we have Young modulus also as stress over strain. So we are bringing this guy, we are bringing him to what? Thermal stresses and strain. You know, what we've been saying this morning is the concept of thermal, meaning temperature. Now, I want to look at stresses and strain. This is what we are relating to it. Right? Now, we are not saying from equation 1, we have change in length is equals to linear expansivity. Every material has its linear expansivity. Change in length is equal to linear expansivity times the original length times change in temperature. So this is equation 1. From equation 1, let's get strain. By formula, what is strain? Come back to this place. Strain, this is what? Change in length over original length. From equation 1, make change in length over original length subject of the formula. That becomes what? We have that change in length over original length is equals to linear expansivity times change in temperature, which is equals to what? Strain. Call this equation 2. Meaning that when it comes to thermal stresses and strain, this is your formula for strain. This formula is the product of the linear expansivity times the change in temperature. This is thermal. What do you call this strain? Thermal strain. Thermal what? Strain. Thermal strain. Now, I've seen the concept behind strain as far as temperature is concerned. Now, moving on, let's look at thermal stresses. Let's look at what? Thermal stresses. Mind you, we have stresses in two forms. The first one is case 1, while the second one is what? Case 2. You know, a stress has been induced. Due to the result of this stress, we have change in length. Meaning for case 1, the type of stress by formula, it is what? Change in length. So that is, if the question says that calculate the free expansion, you are saying you should calculate stress. By stress, change in length. This is the formula. Are you getting it? Yes. This is the formula. But for this guy, what's the formula? Let's see that. Now, recall from here we said we have Young modulus. Young modulus is equals to stress over strain. We have E is equals to stress over strain. Make stress the subject of the formula. Meaning the stress induced in case 2. Make it the subject of the formula. Meaning you have stress is equals to strain multiplied by E. Call this equation 3. Let's substitute values. Substitute equation 2 into equation 3. You know I'm substituting, right? Because from equation 2, I'm having that strain, or you say thermal strain, is equals to linear expansivity times change in temperature. Meaning substitute in equation 3. Equation 3 becomes thermal strain, or it becomes stress is equals to this, right? Multiplied by E. Call this what? Equation 4. We are under what? Thermal stresses and strain. By thermal stresses and strain, meaning temperature. So, right, your thermal strain, your thermal strain is equals to what? By formula, linear expansivity times change in length. Right? Your thermal stress is equals to what? Linear expansivity times change in length times Young modulus. Right? By formula, your stresses.
This is temperature, right?
What's that?
Temperature.
Change in temperature. What did I say? I'm sorry about that. Change in temperature. Change in temperature. I said this very one is what? Your thermal, your linear expansivity times what? Change in temperature. This second one is what? Your linear expansivity times change in temperature times Young's modulus, right? What is another name we call Young's modulus? Modulus of elasticity. Right? Modulus of elasticity. We are going to see the difference between modulus of elasticity and modulus of rigidity in torsional equation. We are going to see that. But when we get here, we see that. You know, we are doing stresses and strain now. We are doing stresses and strains. You know, by stresses and strain, we are representing stress as sigma, right? We are representing stresses as what? Sigma, and strain as what? Epsilon. Now, when we get to torsion, say we want to derive the equation of torsion, you now call the stresses that you know here as shear stress. Why you call the strain that you know here as what? Shear strain. So the ratio of shear stress to shear strain will give you modulus of rigidity. We give you what? Modulus of rigidity. So we do all this that I'm saying. We are going to see the concept when we start deriving the equation for torsion. Because I believe that by derivation, the formula stick to your head better. Are you getting me? When you derive a particular equation, the formula for that equation, it sticks to your head better. So with that, when we get to torsion, we are going to derive the formula. We are not just going to use the formula saying we are having T over J is equal to this to that. We are not doing that. We are going to derive it. Are you getting me? So that's it. Just know that. All right. Any questions so far? Any questions so far? Okay, we said this very guy is for strain. This one is for my what? Prevented stress, right? Hope I'm communicating.
Yes, sir.
Then the next one is my what? Free expansion, meaning equation 1. Meaning equation 1. Meaning equation 1. Now, all of this, let's see how. Okay, we've even done the derivation already. We've done the derivation. But, you know, I said we are going to understand this topic in two forms. The first one is what? the practical explanation saying we have a rod, we have this, we have that. Why the other one is what? By linear expansivity, right? You know, by linear expansivity, we said linear expansivity by formula, linear expansivity is equals to change in length over original length times change in temperature. Change in temperature. Now, call this equation 1. From equation 1, cross multiply. What do you have? Linear expansivity, length, change in temperature is equal to change in length. Call this equation 2. From equation 2, okay, you can see that this equation 2 is the same as what we have here. Can you see how it works? Meaning up to this level, the derivation we did from this very equation 1 to this last end remains the same. It's what? It remains the same. We derived this, we got all this equation using the practical explanation behind it, saying that a material has its linear expansivity, it has its length, it has change in temperature, right? So that's how we derive all this. The other one is that using linear expansivity, by formula, this is linear expansivity, say equation 1. From equation 1, make change in length is subject of the formula, we have this. So meaning from equation 2, all your derivation remains the same. All your derivation remains the same. Meaning we've understood this concept in two forms, or you say in two ways. The first one is the practical illustration, while the second one is what? Linear expansivity. Any questions so far? So all these formulas, these are what we'll be using in calculation. These are what we'll be using in calculation. Now let's take down our first example. Question says that a steel rod